In this section, we are going to begin talking about a concept known as dynamic programming. Dynamic programming is mainly an optimization over plain recursion. So wherever we see a recursive solution, meaning that we have repeated calls for some input, we can typically optimize that recursive solution by using dynamic programming. Now, I'm not going to spend too much time on dynamic programming, but it is a concept that I wanted you to be familiar with. So to start off, let's do a simple problem that we already know, which is the Fibonacci sequence. So we did this in the recursive section, but there is a dynamic programming solution to this as well. So we will create our function and we'll pass in an I32 and return an I32. So we will create a couple of variables called A, B, and C. So we'll say let mute A, let B equals 1. It helps if I assign 0 to A. And then we will say let mute C, and then it's going to be of type I32. So here we don't have to do any of our checks that we did in the recursive solution. We can do a simple for loop, and we don't care about where in the for loop we're at, so we'll just designate it with the underscore, and then we'll say from 2 and then include all the way up to the value parameter that we're passing in. That way we also include that value, and then we will simply say C equals A plus B, A is equal to B, and then B is equal to C. And now we want to return B. So probably looks a lot different than our recursive solution, but we can test this out to make sure that it works properly. So we'll implement a quick test case on it. Mod test, use super, bring everything into scope, and we will say we have a test case where we want to test our Fibonacci out. So in here we will say assert equals, and we will say Fibonacci of 9, and the result should be 34. So if we run our test, try adding, that would help, for n. Now if we run our test, we see that our test passed successfully. So again, this was a very simple solution, and I wanted you to get familiar with what dynamic programming is. And again, dynamic programming is used as an optimization over plain recursion. So wherever we see a recursive solution, we can typically optimize it using dynamic programming. And what we did here is we took our recursive Fibonacci solution and turned it into a dynamic programming solution, and we see that it works just fine. So now that we have a general understanding of what dynamic programming is, we will look at a couple of additional problems to really solidify our learning on dynamic programming, and we will start with looking at what the longest common subsequence is in the next lecture. In this lecture, we are going to go over what the longest common subsequence is. And it's a very simple concept to understand. It's taking two strings as input and figuring out what their longest common subsequence is. So what I mean by that, so let's say we have two strings. And for our first string, we'll keep it simple, say A, B, C, D. And then our second string is D, E, F, and G. Well, in this case, our longest common subsequence is D, because we have a D here and we have a D here. And then in another example, let's say we have A, C, I, and O, and then down here we have B, O, I, and Z. Well, we see that we have an I and an O here, and an O and an I here. Therefore, our longest common subsequence is O and I. Right? So overall, the concept there is pretty easy. So it's not too difficult to kind of understand what we want to do. But adding in dynamic programming gives it like that little extra layer of complexity. So for us to kind of figure out how to code this and visually code this, because we're not using recursion, we can use 2D arrays. So it's going to basically be one big grid. And we'll say that our sequence is A, B, C, D, and E. And then up here, we will say that we have A, C, and E. So we'll create our grid right here. And finish it up. Put one. That was a bad line. And we got our grid now. So the first thing that we want to do is basically initialize the outside with all zeros. That way we know, hey, we've exhausted all possibilities in here. We completely enumerated every possible scenario that we can in here. So the first thing we want to do is we're going to start up in this index right here. So we see that we're comparing A to an A, which means, yes, they match. So we can denote this by putting a 1. Well, when you have a match, you're going to move diagonally. So we know we have something here that can contribute to our longest common subsequence. So we want to move diagonally. So we're done with the A's now. So now we are comparing B, C, D, and E to C and E. Well, we see that B and C obviously don't match. So we can put a 0 here. And when you don't have a match here, then you want to check to the right and you want to check down. Well, we see that B and E do not match, so we can put a 0 here, and now we want to move down. So we're done with B. So now we're at C, so we're comparing C, D, and E to C and E. Well, we see that we have C and C, so we put a 1 here, and now that we have our 1, we're going to move diagonal again. So now we're at the D level, so we're going to compare D and E to E. So we know that D and E are not the same, so we put a 0 here, and we either move to the right or we move down. Well, we see that we already have our 0 here, so we know we're not going to the right, and now we got to move down. So now we're comparing E to E, which means that we have a 1. So now we either go to the, and since we have a match, we move diagonally. And since we see we have a 0 here already, we're done. So for us to figure out our longest common subsequence, we're going to go from, we're going to do 0 plus 1, because we're going to move up our path that we just traversed down on. So we're going back up. So we go 0 plus 1, so this would be our E. So now that we're here, we go up, we see that we have a 0, now we're going to go back over to our 1, which is going to be our C. So now we have that, so that would be another plus 0 plus 1. And then we're going to do another we're going to move up 1, which is going to be a 0, and then we're going to move diagonal 1, which is going to be our last A. So currently our longest common subsequence is EC and A, and if we want to put this in the order in which we traversed it down, we can just simply call reverse on it, and now we have our longest common subsequence of A, C, and E, which you don't have to reverse it. I just like to do it personally. So now we have A, C, and E, and if we look at A, C, and E to A, B, C, D, E, we have our A, we have our C, and we have our E. So we definitely have the correct solutions. So again, we start in the top left corner, we work our way down, and then once we know that we have enumerated every possibility, we work our way back up to rebuild our longest common subsequence. So now that we have a really good understanding of how this algorithm works, we're going to go implement it in the next lecture. In this lecture, we are now going to go over the implementation to the longest common subsequence that we discussed in the previous lecture. So, we're going to start off with the function initialization, longest common subsequence. And remember, we want 2 strings, so we'll do 2 string slices. And we want to return a string with our longest common subsequence given to us. So we want to store all the characters into a vector. So for us to do that, we can say let a vector of type char equal a dot chars dot collect. So now we just stored all of our a's into a vector, and we want to do the same for B. And so here we are storing all the characters into the vector. Next, we want to store the links of our vectors. So we can easily create it by saying let length A and length B equal to A dot len and B dot len. So we want to store the links. And then lastly, or not lastly, next we want to say the solution is from within I to J is the length of the LCS. We'll say LCS, longest common subsequence. And then between A of 0 to I minus 1 and B from 0 to J minus 1. So for us to create this solutions vector that we want here, we need to use the links that we generated here. So we want the solution to be a vector, and it's going to contain a vector, and this vector is going to be from 0 to B plus 1, and our other vector will be from 0 to length A plus 1. And I realize that I need to put those there, and let me add that there. Alright, so we just created our solutions vector of lengths of A from 0 to 1, j minus 1, and 0 to j minus 1. Alright, so now we could begin traversing our 2D array from top to bottom. So we want to enumerate all of our possibilities for that. So we will say for I of m of I, so we want two iterators here, and a dot iter, and then remember we want to enumerate, so luckily Rust gives that to us. So we want to enumerate all the possibilities, and then for j and m of j, and we want to do it the same thing for b, so iter dot enumerate. So now we're beginning to traverse down. So if m of I is equal to m of j, there is a new common character. Otherwise, take the best of the two solutions at I minus 1 to j and I to j minus 1. So if m of I is equal to m of j, there's a new common character. Otherwise, take the best of the two solutions at I minus 1 and j and I of j minus 1. So we can very quickly implement this by saying solutions of I plus 1 and j plus 1. So we're just moving our index in the array, equals if m of I equals if m of j. So if the solutions are the same, or excuse me, if the characters are the same, then we want to say solutions. I keep saying solutions. Solution I j plus 1. So we are denoting it that we have a common character by putting the 1 value there. Okay, so now we say solution of I, and now we go j plus 1 dot max solution I plus 1 and j. And this max method here that is given to us inside of the vector class is going to compare and return the maximum two values. So we're going to compare I and j plus 1 to solution of I plus 1 and j. So now we just implemented in this portion of it. And so once we've done all that, well then we have completely enumerated our 2D array from top left to bottom right, or basic what we did in the previous lecture. So now we want to go from the bottom up. So we want to reconstitute the solution string. So we want to get our solution string back from the links. So remember, if the value is 1, then that means we had a common character. And so we want to take that character and add it into our solution string, if you will. So to do this, we'll say let result of a vector of type char equals a new vec, and we'll say let mute I and mute j equals to length a and length b. So while I is greater than 0 and j is greater than 0, we want to traverse from the bottom up. So if if a of I minus 1 is equal to b of j minus 1, then we want to push this result because that means we have a common character. So we will say push a of I minus 1 And now we want to traverse up the array. So we're going to decrement. That way we go back up to the top. Else if solution of I minus 1 and j is greater than solution of I and j minus 1, then we just want to move up the I value. Else, our last case, we just want to move up the j value. So if they match, move up and decrement both of them. If I minus 1 and j, if this index is greater than this index, then we just decrement I, otherwise decrement j. So again, that is just us traversing back up from the bottom to the top of our 2D array. And then, as I said, I always like to reverse my string. That way it's back in kind of the order in which the string was presented to us. And then for us to turn it into our string, we will say result.iter and collect. And I believe that is all we have to do. So let me do a cargo build just to make sure that it runs. It looks like we're missing something. What are we missing? Get rid of that. That way it is actually returned. And line 45, I need to add our semicolon. How about now? Now we're happy. Alright, so let's add in our test cases now to verify that our LCS function works. And we'll add in a couple of test cases to kind of vet it very good. So longest common subsequence. And so we'll have an empty test case. So we will assert equals on our longest common subsequence. So if they pass in 2 empty strings, then we expect an empty one to be returned. And we will do a couple more empty ones where we actually pass in something. We expect nothing to be returned, and if they passed in the first parameter, we would also still expect nothing to be returned. Some more that we can do is we can actually do some simple ones. So we can have A, B, C, D. We expect A to be returned here. A, D, C, B. If we did B, we would expect B to be returned. And lastly, if we did QWERTY, and let's say we passed in RT, then we would expect RTY to be returned. And then let's do a couple more complicated ones. We will say A, B, C, D, GH, and we'll pass in AED, FHR, and in this case we would expect ADH to be returned. And our last test case, we'll do AGGTAB, so that way we have some repeating characters in here, and we'll have GTX, GXTX, AYB, in which case we would expect GTAB to be returned. So let's just double check this to make sure we are returning everything correctly. So we have GTAB, GTAB, so we're looking for ADH, we have ADH, ADH, RTY. So yeah, so everything looks pretty good here. So let's run our test cases and see what we get, and everything is passing successfully. So we successfully implemented in our dynamic programming solution to the longest common subsequence, and hopefully this made sense to you. Again, with it being dynamic programming, sometimes it does add an extra little layer of abstraction, in my opinion, and complexity to it. So if you have any questions about my solution or the algorithm in general, or just dynamic programming in general, please feel free to ask them in the Q&A section. And in the next lecture, we will look at one more dynamic programming solution before we move on to our next data structure. In this lecture, we are going to begin discussing the maximum subarray. So the maximum subarray is going to be finding the subarray that is at least one value which has the largest sum. So, and the one rule to this is a subarray is a contiguous part of an array. And if you don't know what that means, I will explain it in just a second. So, let's imagine we have an array with -2, 1, -3, 4, -1, 2, 1, -5, and 4 again. So this is our array. Let's split up our values. So a subarray is a contiguous part of an array. So that means that the values are in order, right? So -2 to -3, that's not a subarray because you skipped over the 1. So 2 to 1 would be 1, 2 to 3, 2 to 4, 2 to -1, and so on and so forth, all the way over here to the end. So what we want to do is find a subarray in this array which is at least one value with the largest sum. So there's a couple of different approaches that we can look at, but let's try to do one of the most efficient, and let's go with the linear solution. So we're going to look for the linear solution. And what we'll do is we're going to start at -2, and so obviously we have -2 here. So we have -2, and then if we go to 1, so if we added 1, well, we're still at -1, but 1 is obviously greater than -2, so there's no point in even worrying about that -2. So we'll just go ahead and discard this value because we know that it doesn't make sense to start there if 1 is already greater than that 2. So we'll move our index over to here, and now we're starting at 1. Okay, well now we have a -3, so we'll add plus -3, which means we are at -2, and now we're at -4. So now we have plus 4. Well, 4 again is greater than -2, so it doesn't make sense to start out at this 1 and then add in this -3. So we have another negative prefix. So we'll just go ahead and discard all of these values because it doesn't make sense to include them when we can start out at 4 right here. Okay, so we start out at 4 now, and we add 1. So we say plus -1. So now we're at 3. So we bring down this 2. So now we add 2. And now we're at 5, bring down the 1, now we're at 6, and if we bring down this -5, now we're at 1 plus 4 is equal to 5. So even if we did this entire subarray, we see that our greatest value here is 6. So for this array, our longest contiguous subarray, or excuse me, our longest subarray, so our maximum subarray would be 4, -1, 2, and 1. And this would give us 6. So we don't have to worry about any of these other values here. So in this case, we are done. So if we look at this, there was a common kind of theme that we were looking for. So we were removing negative prefixes, right? So what does that mean? It means that it doesn't make sense for us if we have a 1 value here to start out with a -2, so get rid of it. Or in this case where we had our 4, well, we had a -2 here, so that -2 was a prefix to the 4. So it doesn't make sense for us to start out with this -2 that we got from these two values. So we just kind of slide our index down until we find that value that doesn't have a negative prefix, and then we begin kind of enumerating all the different subarrays that can form from this value, or this starting index, which we were able to conclude was this 6 here, which in turn this ended up being our maximum subarray. So what I want you to do is I want you to take some time to try to implement in your solution to this maximum subarray problem using a dynamic programming approach. So don't use recursive solution, and if you have any questions or you get stuck, please feel free to ask them in the Q&A section, and in the next lecture we will go over my solution to this problem. In this lecture, we are going to go over my solution to the maximum subarray assignment assigned in the previous lecture. I hope you had a successful attempt at creating a solution for the assignment, and if you have any questions about my solution, please feel free to ask them in the Q&A section. So I went ahead and kind of set up the function that we're going to use. Obviously we need to pass in an array here, so I'm going to do mine of type i32, and then in order for us to return the maximum subarray value, we want to return an i32. So I'm going to use a temporary array to kind of store some values. That way I have a little bit of room to work with, and we want to just go ahead and assign in a value into that temporary array. That way we have at least one result, and we want to create our result array where our answer, or our result variable, which is going to be the answer that we return at the end of the function. So since we already started out at index 0, we can say for for I and 1 to the length of the array, and then if temp of I minus 1 is greater than 0, so we do not have a negative prefix here, then we want to say temp of I is equal to temp of I minus 1, and plus the next value in the array that we have passed in. Otherwise, temp of I is equal to array of I, in which case we are going to just go ahead and move our index up 1. And then for our result, we want it to be equal to the max value of our temp of I. So remember, from the longest common subsequence, max is going to compare result to temp of I, and whoever wins that comparison, whoever is greater, is now going to be assigned to the result variable, and lastly we want to return our result. So this is all we actually have to do for the maximum subarray. So let's create some test cases to make sure that it all works. So we will test it out. So let's create a test, fn test max sub array. So we will say let array is equal to a vector, and we will say 1, 0, 5, and 8. We'll go non-negative to start, and in this case, if we call max subarray and pass in our array, we expect what is 1 plus 0 plus 5 plus 8, 13, so 14. That is what we would expect to be here. So we have 1 plus 0 plus 5 plus 8. So that's a very simple test case. Let's do another one. Let's say let array2 equals vector, and we'll do some negative values in this one. -3, -1, -8, and -2. And here we expect to see only -1 returned, because nothing greater than -1 can be added on to this. So we would expect assert equals of our max subarray of our array2 to be -1. Do another array, and we'll make this one have a couple of different mixed matches between negatives and non-negatives. So we will say, let's go -4, 3, -2, 5, and -3. So in this case, we would expect it to be -3 plus a -2 plus a 5, which equals 6. And we don't have -3, it's regular 3. Yes. Alright. So we'll do our assert equals here, max subarray on a reference to array3, and we would anticipate 6 being returned. So these are 3 pretty good test cases. So if we run them, we see that they pass successfully. All 3 of them do. So it looks like my implementation of the max subarray is working correctly. So again, I hope you enjoyed this assignment, and I hope you enjoyed learning about the concept of dynamic programming. If you have any questions regarding dynamic programming or my solution to the max subarray, please feel free to ask them in the Q&A section, and I will see you in the next section when we start discussing the graph data structure.